Hi everybody, welcome back. Sorry about the little mishap before. So this is not podcast 3.02 because we had to finish it at 3.03, and I'm going to hop back down to finish 126. So we're going to hop right to that slide. Actually, I'm going to hop right into doing it again, as if I didn't before. Okay, so what we were looking at was question 126, and I want to write down the equations we're going to use for this. So the equations that we had, I'm going to flip the order of them. Originally, it started with the end, and we're working backwards. So I'm going to start with, let's put them in the same order. 4NH3 plus 5O2 yields 4NO plus 6H2O, 2NO plus O2 yields 2NO2, 3NO2 plus H2O yields 2HNO3 plus NO. And I'd like to point out that all of these are balanced already, so that's nice. And we're starting with 1.0 E6 kilograms of HNO3. And we want to convert it into NH3. I'm going to get rid of the kilograms right away. I hate those units, so I'm going to go ahead and make it 1E9 grams HNO3. And again, the way my little formatting guide to do this is I'm going to go from HNO3 to NO, then from, NO2, then NO2 to NO, then NO to NH3. So I'm starting out with grams, so I'm hating grams. Whatever unit I have, I hate. So grams of HNO3 on the bottom, and moles of HNO3 on top. And it's going to be 1. And then I get out my calculator, find the molar mass of HNO3. So 1.01 plus 14.01 plus 48 is 63.02. And that's the molar mass of HNO3. Now I'm in moles of HNO3, and I want to go into moles of NO2. So I'm going to put moles of HNO3 on the bottom to cancel that unit, and I'm going to put moles of NO2 on top. Remember, you'll always go through moles. Always go through moles, always go through moles, always go through moles. And this is where the coefficients come into play. I need a relationship between nitric acid, HNO3, and nitrogen dioxide, NO2. And the coefficients tell me that ratio. There are 2 HNO3s for every 3 NO2s. So the coefficient tells me the ratio for those things. So whenever you go moles over moles, you have to use your coefficients. Then I want to get out of moles of NO2, so I'm up into the middle equation now, and go into moles of NO. So right now I'm hating moles of NO2, and I want to go into moles of NO. And again, I'm going to look at my coefficients for a relationship between those two. So note, this time I'm looking at the relationship, and if I number these equations, A, B, C, I guess it would be lettering the equations. Equation B is the relationship I'm looking at, so my coefficients are 2 and 2. I would not use my coefficient in equation C with a coefficient from equation B. They're different equations. They're different relationships. Okay. So now I'm in moles of NO, and I want to convert from moles of NO into moles of NH3. So 4 moles of NH3 and 4 moles of NO. And the question way back when asked for mass. So now I'm in moles of NH3, my golden desired thing. So I'm going to get out of moles of NH3 and go into grams of NH3. 1 mole is, go to the periodic table, 14 plus 3.03, 17.04. And then I'm going to run this through my calculator. 1E9 divided by 63.02 times 3 divided by 2. And then times 2 over 2 times 4 over 4, that's multiplying by 1. So then times 17.04 and this would give me a really big number I wish was in scientific notation on my calculator. So I'm going to dummy it first, 405,585,228.4. So I'll put this in scientific notation, 1, 2, 3, 4, 5, 6, 7, 8. So 4.1 E8 grams of NH3. In this case, I went to 2 sig figs because my starting number, the 1.0 times 10 to the 6, had 2 sig figs. Of course, I would take 4.06 E8 grams of NH3 because that is 3 sig figs, which is always right. All right, let's try the next one. I hope. Come on, change slides. Come on. Number 134. Ooh, acetaminophen, which is the wannabe aspirin, is produced in the following steps. Blah, 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 blah. The first two reactions have an 87% and 98% yields, respectively. The overall reaction yields 3 moles of acetaminophen product for every 4 moles of C6H5O3N. What is the percent yield by mass for the overall process? What is the percent yield by mass for step 3? The overall reaction yields 3 moles, so C8H9O2N. C8H9O2N. I'm just trying to identify these. There's so many C's and H's in here. So the over 3 moles of acetaminophen product for every 4 moles of C6H5O3N reacted. So that's the first one right here. So looking at this, this is at least nice that the overall reaction is 3/4, right? 3 moles. Oh, I should look and see how my coefficients go. So looking at this, this has a coefficient of 1, and then that has a coefficient of 1. And then this product, Chonkel, turns into C6 Chon. And Chon here has 1, and Chon here has 1. So luckily, everything has 1 coefficient. So then the mole ratio things, I'm going to say, of course, you would at least think about them, but they're all going to be 1/1. So my overall yield is 75%. So I've just answered B. What is the percent? Oh, percent yield by mass for step 3. That's not right. What is the percent yield by mass for the overall process? A is 3/4 times 100%. This was where some people would have lost points because you wouldn't have shown any work. What is the percent yield by mass of step 3? Okay, so what I have here is I can start with 100 things, right? So I'm going to start, let's just say I have 100. And step 1 is an 87% yield. So that means I would get 87% of it. So times 0.87. And that would give me an answer of, I almost reached for my calculator, shame on me, 0.87. The second step has a 98% yield. So that means 0.87 would get 98% of it times 0.98. This one I am going to cheesily use my calculator. 0.87 times 0.98 is going to give me 0.85. Give me my 6. Then I know this times some percentage is going to equal 0.75. So to solve for x, all I do is I take 0.75 over 0.8526. This, of course, would be something you would not want to squeeze in on the question, but you get the idea. 0.75 divided by 0.8526, and it is 87.96622, whatever it is. So if I'm going to give this 3 sig figs, I would give it 88.0. If I were to give it 2 sig figs, I guess I would give it 88%. So percent yield by mass for step 3, x equals 88%. And really x equals 0.88, but you get the idea. So there's that. Come on. Answer the following question about a cure contains only Chno. So here's another combustion problem. I want to do yet another one to make sure that you guys are a little bit more comfortable with this. So this is an actual AP problem. So again, I'm going to start with Chno plus O2 yields CO2 plus H2O. This is what some people were struggling with a little bit last night too. This was the online lab type thing. So I found that 0.7549 grams produced 1.9061 grams of CO2 and 0.3370 grams of H2O. Calculate the individual masses of C, H, and O in the sample. This is even easier than normally what we have to do. So again, I'm going to do carbon is find the percent of carbon, 12.01 over 44.01 is 0.2729. Sadly, I have that memorized. You might even also by now. So that means 27.29% of CO2 is carbon. So I'm going to take that percentage times my mass of carbon, and this will give me my grams of carbon. 0.2729 times 1.9061 gives me 0.52017 grams of carbon. And that is this is the individual mass of C, 0.52017 grams of carbon. H, doing the same thing for water, 2.02 over 18.02 equals 0.1121 times, my decimal points there, times 0.3370. So again, I found the percent hydrogen in water, and then it's 11.21%. So 11.21% of 0.3370 is water, and of means times. So 0.1121 times 0.3370 is 0.03778. Now to figure out oxygen, and since this is just Chno, what I have left over would be oxygen. So oxygen equals my starting number, 0.7549. Where did that number come from? You see it up there on top? So 0.7549, and that was from the problem. Minus 0.52017, which is my carbon, minus 0.03778. So really what I'm doing is I'm doing Chno minus C minus H equals O. So let's do that. 0.7549 minus 0.52017 minus 0.03778 equals 0.1970 grams of oxygen. So that's part one. Part two is determine the empirical formula. So what I'm going to do is convert all of my masses into moles, because empirical formulas really are moles of things. So 12.01 is the molar mass of carbon. That's 1 mole of carbon times dividing bar 0.03778. What am I doing? I wish it said an erase. 1.01 grams of hydrogen. Just make the line longer, pretend that didn't happen. And 1 mole times dividing bar 16 grams of oxygen and 1 mole. And again, those little g's on the bottom, or little g stands for grams and little g stands for go to the periodic table. Now, if we're lucky, these will turn out to be whole numbers, but we already know that's not going to happen. So to do carbon, 0.52017 divided by 12.01 would be 0.04331. For hydrogen, 0.03778 grams of hydrogen divided by 1.01. I hate dividing by 1, it's the same thing. 0.03741. And then 0.1970 divided by 16 is 0.0123. And then what I'm going to do is, because these are moles and I want them to be whole numbers, I'm going to divide by the smallest number, 0.0123. And this will make them whole numbers. So 0.04331 divided by 0.0123 is 3.5. Yay, a nice number. 0.0374 divided by 0.0123 is 3.0. Yay, a nice number. And then this is 1. So these are nice numbers, although this is a decimal point. So we're going to multiply everything by 2 to make it a whole number. So if I multiply this by 2, the decimal goes away. So I'm multiplying everything by 2. So that leaves me with 7, 6, 2. So it's C7H6O2. And that is your empirical formula. Nice was a thing we're going to learn. Limiting agent. I use some kind of crazy one now. I just get a limiting agent. Come on. Okay. So limiting rate. Usually when we have A plus B yields C, and I use my dumb tricycle analogy. If I ask you if I have 6 wheels, how many tricycles can I make? Or how many tricycles can I make? And you'd say 2, and I go, not if I don't have any frames. So if I have 6 wheels plus 0 frames, all I have is crying children. Okay. So that's the basis of it, is usually you're short one thing. And let's look at the general process. Just like always go through moles. Convert moles of each reactant into product. So you're going to convert it into moles of product, or whatever the final amount is. So if it asks for grams, convert it into grams of each product. If it asks for liters, convert it to liters of each product. Whichever reactant produces less product is the limiting reactant. Right? So remember, if I said I had 6 wheels plus 1 frame, I could make tricycles, right? I can't make 2 tricycles. This would make 2. This would make 1. How many can I make? I can only make, of course I said 1 and wrote 2. This can make 1. How many tricycles can I make? Only 1. So whatever one produces the less is the limiting reagent. So frames would be my limiting reagent here, meaning if I add more frames, I make more tricycles. If I add more wheels, I make more nothing. Okay. The reactant that produces the most product is the excess reactant, which is abbreviated XS. Oh, how clever. Let's do a real AP problem. Answer the following questions that relate to chemical reactions. Iron 3 oxide can be reduced with carbon monoxide according to the following equation, blah, 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 blah. 16.2 liter sample at, we're going to pretend that STP, because then we know, and you'll hear my rant later on about how 22.4 liters does not equal 1 mole, but that way we know 22.4 liters equals 1 mole. It's combined with 15.39 grams of Fe2O3. How many moles of CO are available for the reaction? This is an AP problem. Really? Really, 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 really? 16.2 liters of CO. Now, this is mean because we barely talked about this in class. Liters of CO, 1 mole CO. How many liters are in a mole? 22.4 if you're at STP. And we're pretending that we are. 16.2 divided by 22.4 gives me 0.723 moles of CO. What is the limiting reactant for the reaction? Justify your answer with calculations. So what I'm going to do, notice again the sequence pair is balanced. Let's go ahead and start with CO since we've got the number. 0.723 moles of CO times dividing bar, moles of CO. And the limiting reactant, I kind of preview into number 3. It's how many moles of iron are formed. So I'm going to go ahead and convert that into iron. I can convert it into anything, but I'm going to convert it into iron so I can answer number 3 by doing number 2. So 0.723 moles of CO. I'm going to convert that right into moles of Fe. Oh my goodness, this has almost no stop TP problem. 2 moles of Fe, coefficient, moles over moles, use coefficients, and then 3 moles of CO2. I'm sorry, CO. So, calculator, that answer's still up there, times 2 divided by 3, and I get 0.42, 482. Moles of Fe. Now, I don't know if that's a limiting reactant or not unless I convert Fe2O3 into moles of iron. So I know I'm given 15.39 grams of Fe2O3 times dividing bar. Hating grams of Fe2O3. I'll always go through moles, moles, Fe2O3. Now I don't have moles over moles, so my number for moles is 1. And little g stands for grams, and move to the periodic table. And iron is 55.85. So 55.85 times 2 plus 48, which is 3 oxygens, and I get 159.7. So that gives me my moles of Fe2O3, and I want to convert that into moles of iron. Times dividing bar. Moles Fe2O3 and moles of Fe. Moles over moles use coefficients. 2 is my coefficient for iron. 1 is my coefficient for Fe2O3. And then just do the math. 15.39 divided by 159.7 times 2. And I get 0.193 moles of Fe. So how much Fe is actually produced? Is it the big one or the little one? I think you guys are old enough to know now that life is pretty mean to us. The little amount is always formed. I don't have enough Fe2O3 to make this amount. So this is the amount that is formed of iron. So how many moles of iron are formed in the reaction? 0.193 moles of iron. Yay. Nice job. Last bit, if it will move to the next slide. Percent yield. Reactions typically do not get 100% yield, and we saw that on one of the previous problems that we did. Why is that? There are side reactions that happen. There are transfer issues. If I pour from one, that's not the word pour. If I pour from one beaker to another, there's stuff stuck on the side. Right? We lose a little bit. And that happens. Incomplete reactions. In order for a reaction to take place, A must actually hit B. And it's got to do more than actually hit B. It's got to hit B in just the right way. So if you think of it like hitting a home run in baseball, you got to hit a home run in baseball hitting it just the right way. So they have to hit perfectly. And maybe they don't hit perfectly. Maybe they don't hit enough energy. Some people just aren't strong enough to hit a home run ever. Sorry, Molnar. So both of you. So that's what you got. You calculate the percent yield in your actual yield. This is your lab number, divided by your theoretical calculated. I'm going to call this the stoich yield. And that's it. We did a little bit of that with, I think it was number 134, and we are done. Sorry this took 2 podcasts, but we're out of here in 24 minutes, plus 8 minutes. Gives us the sad 32 minutes. Sorry to go over half an hour, but that's all right. It was a true joy just doing this. Have a good one, everybody. See you in class tomorrow. Bye.